All right, buffers. Straight out, I'm gonna tell you that we're not gonna really go in depth or in huge detail about buffers. I'm just gonna give you the definition of what a buffer is, and your task is gonna be to identify whether a solution is a buffer solution or not. Um, there are really key important details about buffers that I'm only gonna mention because your book doesn't really care to go much further than that. But a buffer is basically the combo of a weak conjugate acid with its weak conjugate base. This has to happen. You have to have an acid and its conjugate base, but they both need to be weak for you to have a buffer solution. If either or both of these criteria are not met, you do not have a buffer. Now, what's important ultimately about buffers is that they actually resist pH changes. Not to say that you cannot change the pH, but you will need to add a lot of base to increase the pH, or you will need to add a lot of acid to decrease the pH. So the buffers cannot regulate the pH in a system. And in essence, our bodies use buffers to keep the pH of our bodies, in check. Because if your pH changes ever so slightly, your system will be messed up to the point where you could actually die. And temperatures also mess up pH. So if you have a really high temperature, you can mess up the pH of your own body. But at that point, probably the function of proteins is even more altered than your pH is going to be. So, having high temperature is also a bad thing. But in terms of pHs, having buffers in your body and having buffers in solutions is important if you want to keep your pH constant throughout your experiment. All right. Now, as I said, we're not going to be dwelling into the actual mathematics and the actual theory behind buffers. That's something that will come later, usually in the second half of general chemistry. What we're going to do, though, in this class is identify something as being a buffer or not being a buffer. And so we start with the first example here. We have HCl and we have Cl minus. All right, so first look, you see this thing and say, oh, well, the one molecule has an extra H plus, the second one has one less H plus. So the only difference between them is an H plus. They are conjugate pairs of each other. However, HCl is one of the strong acids. And because HCl is a strong acid, this cannot be a buffer. They both need to be weak and they have to be conjugates of each other. So they are conjugates of each other, but one of them is strong. So this cannot be a buffer. Same idea with HClO and ClO minus. The only difference between them is an H plus. So they are conjugate pairs of each other. And if you look at HClO, you realize that HClO is not one of the strong acids present on the list. So that's a weak acid. And looking at ClO minus, that's not one of the bases that I told you to be strong. So that means that they're both weak. They're both weak. They're both conjugates of each other. So this is indeed a buffer. All right, let's do another example. You have HClO and Cl minus. That's a weak acid. This is a weak base. But the difference between them is not just an H. The difference between them is also an oxygen. And because of that, these two molecules or these two species cannot be conjugates of each other, so this cannot be a buffer. All right, let's take a look at another one. It's a little bit tricky. We have H3PO4 and HPO42 minus. At first look, you might say, well, you have PO4, you have PO4, you have only changed the H's. These are conjugates of each other. That's a very common mistake. If you look very carefully, you realize that the difference between them is that you started with three H's, now you only have one. The difference is not one H plus, it's actually two H pluses. And because of that, they are not conjugate pairs of each other. So that and that alone would mean that this cannot be a buffer. So be very careful with that. The difference can only be one H. And speaking of that, if we look at a similar premise, once again, we have phosphoric acid, which is a weak acid. It's not in the list of strong acids, so it's automatically weak. And we have H2PO4 1 minus. That should be 1 minus, not 2 minus. Here we only have a difference of 1 H plus. And because of that, these two guys are conjugates of each other. And they're both weak, so this definitely counts as a buffer. This is phosphate buffer. All right, last one. We have H2O plus hydroxide. We have a difference of 1 H plus, so they are both conjugates of each other. However, hydroxide is one of the strong bases, right? We don't have the metal in here to balance the charge, but the hydroxide by itself is the base, and it is a strong base. Because hydroxide is a strong base, this cannot be a buffer, right? So when you add hydroxide to water, you don't call it a buffer, you just call it basic solution. The same way that when you add a strong acid to water, you don't call it a buffer solution, it's going to be just an acid solution. All right, so that's basically the extent of what I need you to know in terms of buffers. I need you to be able to recognize them as either being buffers or not being buffers. And maybe aside from that, remembering the definition that buffers are substances that regulate the pH and resist pH changes. All right, with all that being said, we have finished the acid-base lecture. Titrations for sure, titrations and the equations, deriving the equations, predicting the products, those are probably some of the most important things of this lecture, but doing the pH calculations and the hydronium hydroxide calculations is the other big thing. So make sure to practice all of that as you will be tested on that particular set of topics. All right, so with this being said, thanks for watching, and I'll see you in the next lecture series.